So I'll do it. So I'm going to talk about what I call pluggable, stackable API implementations, which I realized after the fact, I probably should have called it composable API implementations, because it's actually a more accurate term, because I think we're all used to saying you have an interface, and then you can make different implementations of that interface. But you think of just one implementation that you then serve that interface. And what I'm talking about is you can have multiple implementations happening at the same time. And so I'll get into what I mean by that. Some techniques I'm going to use to plug in those implementations. I'm going to do some type level programming for an extensible foundation. And were any of you in Thomas's type level talk just now? One. Okay, well then you'll know everything. And then a little bit of transformer techniques. If you know monad transformers, you don't need to really know them, but I'm going to steal a little trick that they do. But only a little piece, so I'm not going to have to dive deep into that. And then I'm also going to do just the last little bit of type level program to do some configuration. And that's just because it's fun, not because you actually need it for this. And this talk is based on a talk that we gave at the International Conference on Functional Programming last year in St. Louis. It was in the TIDE track, Type-Driven Development. And that's a link to the talk. These slides will be up and available. And there's actually a better link than that one, so don't take the time to write that down if you're interested. So what I'm going to use as an example is that, from the user's point of view, the API is exactly the same every time. And I'm going to use an example of just a key value map. But what I'm going to do over time is plug in different implementations. A map that first has a cache, and if that fails, then it's going to go through a Bloom filter. And if that fails, then it's actually going to go to the bottom level key value store. And so what's the point of even doing this? The motivation for what we do, I work at Oracle Labs, and we're doing some blockchain research. And one of the things we do is sharding of blockchains. And when you have different nodes come into a consensus verification network, they've got to be brought up to state. And one of the things we do is we give them the key value implementation, but we don't give them the whole thing because it can be gigabytes worth of data. So instead, we just give them maybe just a cache, and then this thing, the key value store, is made out of pages. And if you get a page hit, great, you're in business. If you get a page miss, we go over the network, we ask for the missing page, and then we send the page back, and we also authenticate the page. We prove that the data is absolutely correct. And we do that all by way of this plugin. For today's talk, that's the motivation for why we even did this in the first place. Today's talk, I'm not going to get into the authentication part because it's too complicated for 50 minutes, and I'm not going to get into the paging stuff. I'm just going to get into the technique that allowed us to plug and mix and match all these different types, and it turned out to be very useful. And in the full paper, there's some interesting performance stats. Okay, and most of this talk is all going to be code. So one thing you can do to build, for instance, for this thing I just showed, the cache followed by a Bloom filter. A Bloom filter is basically just something that says whether something's present or not. And if it says it's present, it still might be wrong, but it's pretty accurate, like up to 80, 90%. And if it says it isn't, then it's not there. And it's so you can avoid going to the key value store when you don't need to. So we could build one of these by just declaring a data type, and I'm calling it map, stuttering, just map. And it defines a cache, and this cache is just from something existing. When we built our own caches and our own Bloom filters in what we did, but I'm just grabbing stuff out of Hackage because I'm more interested in the technique than the exact particular implementations of anything. So I've got a cache of keys and values. I've got a Bloom, which only knows about keys, and I've got a map of key values. And if I have that, I can just write by hand, insert. So I say insert takes an ord of k, means the keys have to be ordered. And that's only because the underlying map I'm using requires that. And then you create, then you say insert on all three pieces, because they all got to know that that key is now present in the map. And when you're looking up, you do the usual thing. You first do a lookup on the MMC, which was the cache in this map. Then if it's just, that means it actually exists, and I just returned the just value because their type sector says it's a maybe of the value. If it's nothing, then I look in the Bloom, and if it's Bloom says it's there, then I'll go to the lookup function in the final cache. And even that might say no, but that's just a detail of Bloom filters. And otherwise, it's nothing. So I've just basically hardwired this. This will do the job, and for a lot of things, if that's exactly what you want, just do it this way. What we did is so we could easily change things quickly. So we did a different way. So let's actually build one of those. So I'm calling it a map from int to text. I'm creating a new LRU of just 1024, it's a pretty small cache. And this particular API that I'm using, it's not the one I define, if you give it a nothing, it'll define to some default size. And then the Bloom filter, the way they work is they have a number of hashes, functions, and then a size. And so this is just saying use 3 hash functions that you supply of this size. And the underlying map is empty. So, these slides are actually executable in the sense that every bit of code in here that I show is compiles, and the tests that I've written for them all pass. Because I've had too many slides where there's misspells, there's just plain old wrong information. So this is truth in lending. So this one just says, okay, I looked up one-on-one, it's there, no big deal. And to build this, I tend not to use Prelude, I use Protolube. Protolube is done by Stephen Dill. It's just an alternate Prelude, and it kind of has a lot of things that I like without being too opinionated. So I use that, and then HSpec is just a testing framework. Okay, so that's doing it by hand, which I'm not going to do. The next thing is the foundations. How do I actually then, if I want to make a pluggable and composable way to build these APIs, how can I do that? Well, to explore that space, I'll just go and look at the map itself. So I'll say, what is the kind of map? So :k is shorthand for kind. And it says it is star to star to star. And if you remember the map interface, it was a key, which is the first star, and a value, which is the second star, and the last star is the map itself that is going to, so it's a type constructor. It's saying, give me these 2 types, your types, your keys, and your values, I'll return you a map of that type. So using that information that we get back, I'm going to then define a type class, and I'm using this language extension called kind signatures, and it just allows you to say this. Otherwise, you would just have a C here. And a lot of times kind signatures make things, I think for people learning Haskell, I think that it would be actually easier if functor and everything else had kind signatures. Because right now you just see some magic F's and M's and you say, what are they? If you saw this, you'd have a better intuition. That's a side editorial. So we're going to use a type class as the foundation of this type of signature, kind of signature. And the next thing we need to do is, okay, well, that's the beginning. If we look at the type of insert of existing maps, it says, oh, not only do we need a key and a value and an existing map, and I'll return you a new map with that value inserted, it's saying that it has some constraints on the keys, and it's saying that it's ordered. And that's because this map requires an ordered map. So I need some way in this general mechanism to say, to allow plugins to say what are their constraints. So to do that, I turn on type families and I import GHC ext constraint. So here's that same class that we looked at a moment ago, definition in the beginning. And let's first look at the insert. You remember the insert up here says it's an ord, a key, value, and a map, and then returns a map. This says it's a key, a value, it's a map, but in here, this one said map map K and V. Now it says CKV because I've replaced map by just whatever C is. So I've abstracted out map and just called it C. So it's the, but other than that, this is the exact same signature and one other important piece, and that's this ORD constraint. And I'm saying that for insert, given a C and a K and a V, and remember they're types, what is the constraint for that type? And that's what this type class, what this type family function is. A type family function is a function on types. The family thing sometimes messes me up, and it doesn't mean anything. It just means, actually it does, but it just means it's a function on type. So here's the type. It says the name is map constraint. I call it constraint. Given a C and a KV, those three types return a constraint. So we'll see an example of that in a moment. So this is the beginnings of the foundation. The next piece is that we don't know anything about the implementations that might be plugged in, and they might need to throw errors. And so we're going to allow for that. And the way we do that is we add another type level function, and I'm calling it ERR error, and given a C. Notice it doesn't give, it's not given all three type variables, it's just given the C. It returns some type, and we don't care what it is. And then I got some shorthand, which I just say that I've got a type called error M. Given the C, it returns whatever the type, it returns this type, whatever that returns, and wraps it up in the accept monad, which you can just think of it as either. It's either left or a right. And I use that because you'll see a lot of signatures from here on out where it says error MC of C, K, and V. And that's because now insert, the full definition of it is whatever constraint that this returns, given a C, K, and V, then return a new map, but it might return an error, and this allows for the error. So that is, and here is the complete isMap definition. There could be other functions like adjust and stuff, but this is what I've got so far. So I've got just isMap, this is what you've seen. The map is replaced by a type parameter called C, and it takes three types. There's the error type, the constraint type, and then all of these things. Empty just returns a map, the bottom level map of C, K, and V. And toList returns the list, and on and on. I think they're somewhat self-explanatory. And I added one other thing called stats, and notice I didn't put any constraints on it. It just returns a list of text. And that's just so I can actually look inside and see what's going on. So if I've got a whole stack of these things operating at the same time, and I've worked with them in tests and such, I can go in there and just take a look and see that it's somewhat operating the way I want it to. It's not officially part of a map interface in general. Okay, so now we're actually going to build a few. That was the type class definition, and now we're going to build a few instances. And the first one is real simple, and I'm just going to wrap the existing Data.Map with this type class. I'm going to make it an instance of this type class. And that's the main point of this, is to show how an instance is created and to show how you specify the ORD using that type level function, and also how you indicate no errors and how to return values in the accept monad. So this is it. I'm importing just the regular data map. I'm defining a data type called void, and notice it has no constructors. That means it's impossible to create one of these types. And the reason I'm saying that is because for map, the error, which is a type level function, given that map type, will return a void. And that just basically means it can't throw an error, because there's no way to construct one of these. That's the type of it, but it'll never happen because it can't be constructed. Does that make sense?
Kind of.
When you see a data type and
I get that it won't be able to make an error, but why?
Well, if you look at this particular, if you go to Google and look at the definition of this map, none of its operations throw errors. And so because it doesn't throw an error, there's no reason for this thing to claim that it throws an error. Later, you'll see the next example I have, I'll show one that does need to throw an error. But so for this one, you don't. And so when you don't, that's how you say no, is just say void. And for the constraint, it's saying that given this map of these type of keys and values, it's actually ignoring everything but the keys and saying it needs to be an ORD K. And that's what was going on underneath the covers. So other than that, the empty method of the isMap type class just calls the underlying map. And for toList and everything else, the ones that had possibilities of returning errors, it just calls pure, so it becomes part of this isMap. No, so it's part of the except monad. So that is that. The point of this one was mostly to see how these type level functions are actually returning useful information for this particular instance.
Go over to here, just to clarify the type family stuff. Did you touch on the instance and the type?
Yeah, so this is just an associated type family, which means it's in the only places type family exists is in the context of the type class. So it's like associated with the type class.
When the type families that Thomas was showing were closed, they were all defined at once. So everything that's that's part of them is defined in one place. This one, by definition, is open, and it needs to be because people can define new instances anytime they want, but they need to define the values for these particular type level functions. But they're open.
Quick question about your problem statement. You said pluggable. Do you mean at runtime or at compile time?
Compile time.
So, okay, the next question. You're using type classes here. Why can't you use backpack or something like that?
I've never used Backpack, and I know you can use Backpack for plugging in one implementation. I'm not sure if you could use it for composing implementations, which this one's doing.
I'll probably have to see more, but you could definitely provide multiple instantiations of that same signature with different implementations.
You could do that, but you could only, as far as I know, you can only plug in one at a time. And here I'm composing them, so I'm actually plugging in 3 at the same time, one being a cache, a Bloom filter, and something else. So I haven't used Backpack, so I don't know if you could actually do composition of implementations, but definitely Backpack's a good solution for one implementation plug into an interface. Okay, so now I'm going to show another map, and this is completely made up, and the main point of this is to show that you can throw errors, because none of the other things I'm doing throw errors. And so I'm just saying that I've got the same map that I had before, but I'm wrapping it up in a new type. And that's just so I can define a different instance, because I've already defined one for the regular map. And then I define this data called WE, meaning weird error. And WMap means weird map. So in NP means not present, and OV is overwrite. So all this is saying is when I'm doing a lookup, when there's nothing there, rather than returning nothing, I'm going to throw an error. So, but how can I throw an error? I have to tell the machinery what kind of errors I can throw. So that's where this comes in. It says the error type level function, given one of these W maps, is going to can potentially return these type of errors, and which is WE, this data type. And that way, inside of here, I can then just say throw error. And if it's there, I say pure. The other piece I'm doing is insert. If it's already there, if it's not there, great, I can insert it. But it's a write once map. So if you try to write the same value a second time, well, the same key a second time, it will then throw overwrite. This is completely useless. Well, maybe that write one map might be useful, but the main point of this was, again, to show how you define an error, because we'd already done the ORD thing for a type level function. and this was to do the type level function of an error, and then actually show that the error can be thrown. And this throw error is nothing that I did. Because I said early on that the type of error is this thing. Everything's defined to be ERM, and that's except. So that's where you get the throw and the pure from. The pure means pure in the context of that except monad. Okay.
About that, actually, so type ERR WMAP equals WE.
Yes.
So WMAP is an instance of C, so it's the same type constructor for the instance, which makes sense.
Mm-hmm.
The reason that you can't specify K and V there is because that would make this dependently typed, and there would have to be different kinds of exceptions for each of the types.
Yeah, the reason I didn't is because I hadn't actually thought about that, and I'm not sure if that's true. Let me think about it. I only need to say for the particular map. It doesn't really matter what kind of keys or values it takes. So you're only talking about what kind of exceptions the map in general can, regardless of the types of the keys. So I don't think that really it was necessary for this particular function. If you say the key, a K and the value, see here I'm giving it all three, but I'm ignoring the value here. I'm just saying that OR needs to be K. So unless you use them, I don't think anything's, I don't think there's any dependently typed programming going on there. If there is, I'll be surprised because I don't know how to do dependently typed programming. Well, I'm learning, but it's certainly not under my fingertips. Okay, so now we're going to show this in action. So I'm declaring an empty WMAP, and there's the definition. And then I'm going to say toList on it, and I have to say run except because remember I'm inside of the context of that except monad, so that gets it out of the monad. And I say, and it should be a write, meaning there was no errors, and it's an empty list. Then I do a lookup of 2, and notice this time it got an error, because remember on this particular weird map, WMAP, it's when things aren't present, rather than returning nothing, it's going to throw an error saying not present NP. And left, because it's in the except monad, is the error, the left side. And then when I insert something in, great, I just got an X from it, and I'm doing what you shouldn't do in production code, saying from right, which means I just know it's going to be a write, trust me. If it didn't, it would blow up. And I'm saying show me the stats, and the stats are just 1, meaning there's one thing in the map. And if I try to insert the same thing again, I get an overwrite. So nothing too magic there. Let's do the similar thing, but with a cache. Oh, that was a weird map. Okay. So now I'm going to do a cache. We're starting to get into things that I'm really interested in, and that is I want a cache and a map. This data structure explicitly says what kind of map I want. So I know that the only thing I can do is just have this cache followed by a map. But so I'm saying again, it's a void. There's no errors. Same constraint, ORD K, and to the empty basically creates this data structure and it initializes the cache and then an empty map. And I've got a big to-do here because it's saying just 1000. I've hardwired in that configuration value. And this is something we'll deal with later through another bit of type level programming. But if you were going to do this at runtime, you would have to change the signature of empty such that it could take, you don't know in advance who's going to plug into this. So you'd have to have a way to say for a set of unknown things, I have to know what they are, to supply those values. And you'd have to say that. And then for LRUs, they would have to get that value out. You could do that, and you could do it with lots of different ways. Association lists, and you get lucky with lists, or you could do it with type H lists. But I'm going to do it a different way. So for now, I'm going to leave the hardwire just in there because, well, that's what we have to-dos for, right? Because we always do our to-dos on Friday at 5 p.m. So to lists, there's nothing in the cache, so I ignore the cache and just do to list of the map. And for lookups, just what we'd expect, I say lookup of the key in the cache. H is the cache, and if it's there, then I just return that J. And the pure is remember to wrap it up in the right thing of the accept monad. Insert is similar, where I have to insert it into both of them. Stats, I'm showing the stats of the cache, which is how many elements are in it, what's its maximum size, and then I cons that on to the stats of the underlying map. So this one is interesting, and it works. I say if I create an empty one, it has 0 elements in both the map and the cache, and if I insert something, we see there's 1 in each one. Yes?
Is the cache, like, theoretically, the LRU, is that more performant than the underlying map?
I'm not so sure about this particular cache, because for the talk, I'm just using a cache I grabbed off of Hackage.
Okay.
But
The idea is that, like, if you would use this, it would be more performant than another.
Yes, absolutely, yes. Well, there's another big reason too, which I'm not sure if you were here for this part, and that was the motivation for doing this work. And that's that we do sharding of our blockchain, and we have different verifiers coming in and out. And when a verifier comes in, they need to have the world state of the contract, and you don't want to have to drag all that world state around. And so what we do is we send a cache around, and they might get it. And when they don't hit the cache, they actually hit a page. We have a paging infrastructure, and we go get that page from storage or whatever, and with authenticated data structures, and all that's plugged in underneath. But so in that case, the cache is really going to win. Okay. We did the cache. Okay, let's do the same thing with the Bloom filter. And this is very repetitive now. But yes.
How do you get the updated LRU cache?
Ah, great. That was a fantastic question.
You have to do that. Oh, I see.
Yeah, exactly. But actually, I'm glad you said that, because I meant to mention that. I'm cheating on this, and the only reason, well, let me tell you how I'm cheating first, is what his question was. When you're doing a lookup on a key, you are touching that key. That means it's the most recently used key. So if you've got a cache infrastructure, it's probably going to move that, however it's keeping track of things, it's going to say, this is the most recently one, so the least recently one is now closer to the end. And this particular cache implementation returns both the value and the updated cache. I'm ignoring the updated LRU here, and the only reason why is because it complicates the return signatures, and it's not particularly germane to the main point I'm trying to get across. So, but in a real implementation, you definitely want to keep that updated, to have the updated cache. So I cheated. That was, the answer to your question is I cheated.
That's a load bearing to do.
It is.
Just unsafe before my eyes.
There you go. It's a solution to everything. Okay, so now we're going to do a Bloom, and this looks almost the same. Remember, on the previous slide, we had a cache up here with some sort of cache here and a map here. And on this slide, now we have a Bloom, but the same map. So if we look at this thing, this is interesting. It's saying the error, and I don't think I mentioned this in the last one. Notice these are type functions calling other type functions. I'm saying that the error for a Bloom of 1 is whatever the error is for the map. And of course, if you go all the way back to the map said it's not throwing any errors. But the Bloom, when it's composed on top of something else, it has no idea of the capabilities of the underlying thing it's plugging into. But it also knows it's not doing it, throwing any errors. So great, then I'm going to just say whatever he did, that's what's going to happen. I'm going to do nothing. If they both throw errors, then you'll have to have some way to compose the errors, which I didn't get into here. And one reason I didn't get into is because generally, if the bloom's going to throw an error, you hit the bloom first, so you don't need to worry about what's going on below when you throw an error. Okay, so, and the constraint, notice here, I've changed it a little bit. It's got a little extra, and that is, I'm saying for this bloom, it's the constraint of the underlying map, but it's also saying that the keys have to be hashable, because that is a requirement of the particular bloom implementation that I'm using. Other than that, a lot of this looks the same. We have, to create an empty one, I'm doing the same thing. I've created, but whatever structure this thing needs, and I'm hardwiring it in, which we'll fix later. And for toList, I'm just going directly to the list. The lookup, I first go through the bloom filter, and if bloom says it's there, then I try to actually look it up, and if it says it's not there, then I know I don't have to waste my time. And insert, you just insert it into both maps. So the important thing to notice about these two things we just did is this cache didn't use any intrinsic information about this map. It just called it when it needed to. Same as thing with the bloom version. So rather than actually specifying a very specific one, we're going to abstract the map type into a type variable and make higher order instances. So how do you do that? So once again, like remember when we started this, we looked at the kind of map and we looked at the type of the insert operation. So now we're going to look at the kind of monad, and it says it's a type to type, given a function of type, a type level function of type to type, it's going to return a constraint. So we're going to build something similar that says give all three type level parameters of the map, we're going to return a constraint. And if you look at monad transformers, what they do is they take this guy here and they embed it into a larger one. So you still end up with 4 stars and it returns a constraint. And all that's doing is wrapping a one monad up with another monad. And so we need to do a similar thing, but we need 3 stars instead of 2 stars. And if you actually look at monad transformer, it defines a lift, which just said given a monad, and then given that particular monad, you're going to wrap it up in one more. So you'd have a similar thing with a mismap transformer, but I don't actually define this ismap transformer class. And the main reason why is because for transformers, you don't know what operations each transformer does. They actually disjoint set. Like for readers, you have ask, and for writers, you have tell, and such. And so they're not the same operators. Whereas for the ismap, they're all the same they all have to support the same operation. So I really don't need a lift, and you'll see why that's the case. But I still need this lifting idea of wrapping something up. So this is where we get into the last part of stackable plugins. So they're higher order instances. And so given I'm now calling it a bloom of 2, this looks the same. Before it said there was a bloom of keys of type K. Before, remember, this said it was a map of KV. Now I'm saying it's a C of KV. C is that type to type to type. So now I've abstracted map into this type called C. And then, so I say if, for the instance, if C is a map, then a bloom of C is also a map, where the error of a bloom of C is, just like before, it's the error of the underlying map. But now I'm not saying it's error of map.map, I'm saying it's error of C because I have no idea what's coming underneath. It's not hardwiring in that map. And the constraint looks the same too, but once again, I'm saying the constraint of C. Everything else down here is similar except right here, and that's I'm just using the fmap. So I'm saying if you're inserting and this throws an error, then you're just going to get the error back. Otherwise, it's going to wrap two inserts up into this bloom of 2, which has 2 slots in it. So that's the higher order instance. Okay, wait a minute. Is there something I'm missing on this?
Cheap hashes to do.
Yeah, very good. I think that's what's next. Configuring the bloom filter at the type level. So that's exactly right. Remember for the to-dos we had in there for the basically configuring empty for the different types. So when it's an empty cache, it needs to know the size of the cache. For the empty bloom, it needs to know how many hashes you're going to use in your bloom filter and how many bits you're going to have in your bloom filter. So we're going to do that now at the type level. And to do that, I need data kinds and poly kinds and GHC typelets. And data kinds, well, you'll see what that means in a moment. It basically means that the way I'm using it, you know, we all know the number 10. And you know, you can pass that around to your functions. But with the data kinds, you can make 10 become a type. So you can say type 10. That's like real magic stuff. And polykines, you don't really need to know for this particular talk what it means, and it actually confuse things. So let's take a look. And this is the most complicated part. And back up to it. This part, if you were interested in using this technique, you don't need this part. This is just to do that configuration. If you were happy to hardwire things or figure out a way to pass that information into the empty method, you don't need that. But this is cool. This is I think it's really cool. So what I'm saying is I've got a new type of sBloom, and the S in my mind means sized. It's a sized bloom. And I give it 2 phantom types, and N means the number of hashes, N bits means the number of bits in it, and K is the type of the K. And notice all it's doing, what we did before, it looked like before, it says it's just creating a bloom of type K, and these things are just phantom types that will be used by the compiler later. And then I have this other thing called bloom of, and it is the thing that takes one of these guys, which is the bloom, and it takes a map. And this is similar to what we were seeing before, where you have whatever you're wrapping it with, the bloom, and then the underlying map. But I've added 2 constraints here, 2 types, saying that n hash is a natural number. A natural number is the kind of these types. So it's basically saying if you give it a 10 there, 10 is a type. If the number of bits here is 8096, that becomes a type. You'll see how those get used later. So this instance now says that if n hash is a known nat, and that's just a way to tell GHC, in a certain sense, to get the GHC type inference and unification machinery to line everything up. So I have 2 known nats, that's the number of hashes and the number of bits, and the underlying map is a map, the underlying C is a map. Then isMap of bloom of n hash, n bits, and C is this class. And once again, the error is just the underlying error of C, but I've got some extra things here. The constraint for this bloom is the same constraint, the underlying map, the same hashable, but I also have the known nats of the hash. Now here's where the magic really happens. You know, I've thrown everything away, the insert, because that doesn't make any difference. We just needed to get to empty. I need to create an empty bloom of. And this is the magic right here. I call this extra function bEmpty, giving it 2 proxies, and then I call the underlying map empty, and this looks recursive, but it's actually, because of the type of this thing is CKV, so it's knowing whatever your underlying type is, it's going to call that version of empty. So, but this when you first look at it, you could like, you got a loop going there, but it's not. But anyway, so that's actually a little bit of magic too, and it's because it's type classes at work, and you're actually recursively calling the same kind of the same class, but a different instance. Okay, here's the bEmpty. And there's one magic thing, which I'm hoping Thomas will know. Notice it has the same thing. I've got these known nats. It's given two proxies, the H and the B. And then here's where it actually turns the type level information into runtime values. And that's give me the nat value of H, and that's the number of hashes. And so I give that to cheap hashes. And give me the nat value of B, which is the number of bits. That becomes the number of bits. And that's the same bempty we were always calling before with hardwired numbers. But now it all magically works. The part that I still don't understand is this just says proxy and proxy. This says proxy of H and B and how them used. So I guess they're in order, but how do these two here get lined up with n hash and n bits? Where did I specify, which of all these orders, which one of those got those things to line up correctly? Yeah, I'm not either,
It's
so.
not return, it's inference, right? It's the return signature of the entity you call
Right,
the
it's-
SBLM.
SBLM.
It's literally the only thing that can fit in there.
Right.
So H,
Agent
okay, I see what you're saying.
Proxies have-
Right, and I've already specified it here what that is. Yeah, okay, these two.
Unification happens in the return type.
Aha. So an easy way to test that out would be reverse the return type and see what happens. Okay.
And out of curiosity, map_val is coming from data kinds?
It's coming from GHC typelets. Yeah.
You can do the same with type of strings, it's like numbered symbol and
Right.
symbol.
Yeah. Right. They've got, for all those things, they've got ways in and ways out. So now let's see one of these in action. I'm creating a bloom, and so I'm actually saying empty. And notice now the type is bloom of 3. And remember, 3 is now a type. A bloom of 4096, and then I'm just putting a regular map underneath it. And if I say toList on it, it's right. And if I ask for the stats, the only stats I get of the bloom filter are the number of bits, but at least they match. And which is one way when I was experimenting with this, I switched these numbers around just to make sure that things came out right. Okay, so one last piece, and that is, oh, wait a minute, nope. This one's just going to be a little repetition, and then we'll get to the very last piece. This is the cache, but it's the cache version of the exact same thing we just did for a bloom. And that's that I'm declaring this cache structure, which has an LRU, and then I'm claiming this bigger thing, which has the cache and an underlying map. All of this stuff looks the same, and it's using the exact same proxy trip and a helper function to actually grab those proxy values, turn them into values at runtime so I can give it to this new LRU constructor. So it's the same mechanism. So you'd repeat that if you needed to do configuration and you wanted to do your configuration at compile time. So how do we actually create now a cache, bloom, and map combination? And this is how I've done it. I've declared a type alias called CB, meaning cache bloom. I guess it should have said CBM. But given a bound, given number of hashes, given number of bits, and given a map, I've extracted the map, then return a cache of, and I give it that bound, which is a type, and a bloom of, and it is given 2 types, and the C, which is the final type. So to actually use that, I say, for this particular one, I just want 20 things in the cache, 20 possibilities, pretty small cache, 3 hashes, 4096 bits in the bloom filter, and then the underlying map. So, and then I create one of these by inserting something into it. So if I look at from right, yeah, toList, there is the 2 things, the only value in it. And if I look at the stats, we see that there's one thing inserted after I've inserted something. Out of a possibility of 20 places, there's the 496 bits, and there's the lookup of 1. No, I mean, there's the size. There's one thing in the map. So that is it. And here is the very last piece. That I told you that these were executable slides. The slides compile, every line of code compiled. And then I checked it. You remember all these had these HSpec things and said WM1, which weird map. So it actually, everything compiled and ran. And that's it.
Sorry.
We have 5 minutes for questions.
Great, okay.
Okay, I was just going to make an observation about pushing your configuration up to the type level, like the wooden code design. One neat property you get out of that, I don't know if people are familiar with liquid Haskell, but you can do something like refinements on those configuration values. So you could create a type family which says, takes two natural numbers and says greater than or equal to and return with truthful or falsification constraint. And then you could say that this function only takes a cache which is at least this size.
Oh,
Allow you, which has these properties.
right.
Is that like if you run liquid Haskell on top?
No, you could do that with liquid Haskell, but because you pushed it up like that, you can just use a normal type family, which if the value is true, then the constraint actually fails, so your code won't compile. So you can do
What do you put the failure in case? How do you?
What's just the type family?
Well,
Return the type as a constraint. So then you just constrain the.
You say
Right. The
constraint-
failure would mean it won't compile.
It says, yeah, it won't compile.
Yeah, so
Like,
you,
when you're computing the constraint based on the type inputs, like an actual number of type inputs, you can like compute a constraint and put that constraint in like a function.
What does it actually look like if you make the compiler fail?
Oh, it just won't compile. It'll say, I can't satisfy this constraint. You've given me 4095, but I need at least
Okay.
4096.
Yeah.
right. And what you're saying is that you could specify that directly in Haskell just by
Yeah,
adding a little bit more machinery to what's already there. So you'd eventually give the same number to where it needs to be fed, but it would go through a lot of constraints first to get there. Yeah.
So are you using this in the actual
Yes,
production
yes.
code base?
Yes, on these two links here, the top one is a link to these slides in the code, and the bottom one is the full paper, and the paper talks about more how we use it in the blockchain research we're doing, particularly the authenticated stuff, which is where it really became in handy, because when you get the initial map when you're starting up, you're given basically a hash, which is a fingerprint of the entire structure, even the pieces that are missing. And then later, when somebody sends you pieces because you got a page miss, you can verify that those pieces they're sending you really do fit where they're supposed to be, given you trust the various keys that things have been signed with.
Trees or something?
Yes, exactly. Same idea.
I mean, if you're sending this over the wire, I'm guessing,
Yes.
you're gonna lose some type trouble or.
Well, we're using serial, Cereal. It's the data.serialize. And that basically puts, turns your Haskell data types into bytes, and then on the other end you use the same thing. So you're trusting serialize to do it right, but we actually do signatures too, and CRC checks and all that sort of stuff. So even if it deserializes right, we're checking a lot of various stuff.
Would it be possible to have like a different, like some chains that different client implementations, different languages, as long as you serialized it to the spec that.
Oh yeah, you could. I mean, most people, when they're doing that in Haskell, use ASIN, so everything becomes JSON, and then you can turn that to whatever language you want. Right.
But when the map gets into the Haskell,
Yeah.
all that bits and 36, everything gets.
Well, that part I'm not sure how you would do, and fortunately, I don't have to care.
Yeah, it becomes a bit hard on those kind of interfaces to the outside world.
Yeah. If I was doing a real product, I'd probably have to worry about that more, but fortunately,
Real product, yeah,
What ends
blockchains
up-
are the big deals.
what happens is actually there's something called like a type rep of things, so you can actually serialize, like you can get a hash of the type, and you can figure out the type of the thing at runtime via serialization. So you can like serialize the type representation and then deserialize the type representation, and then GHC knows that, you know, indeed it was 4096 at the type level because, you know, there's a single built-in infrastructure.
All right, you had a question?
Yes, so you use the three numbers as a type. How difficult, I'm just familiar with this part of the library. How difficult would it be to change it to something that you get from runtime, like the args, for example?
To get, you can do that. You can do that.
You can change those literals to int, and that's it, or?
Well, that's what he was doing with the proxy.
Right. Yeah. Basically, you can go from runtime to types and from types to runtime values, and that is possible. The way we do that is with a thing called singletons in Haskell right now. Later in a few years, it'll be a little bit different mechanism, but yes, that is possible, and it really becomes very necessary.
Would you need to change any source code just to transition to runtime?
Well, you'd have to either hand build singletons yourself or use one of the singleton libraries to be able to do that.
In GHC type nats, that's actually that known nat val.
Yeah, that's a singleton, right? Yeah, that's the thing I already had there was kind of doing it for you. So there are some built-in ones like that. I've heard known nat stuff is actually pretty slow, but for what we're using it for, it's just fine. I mean, it runs once. We configure it and we're done. So. But yes, the main question is you can come types to runtime values, values to runtime types. You can go both directions. Okay, I think that's it. Time's up. Thank you for being here. Really appreciate it.